Okay, so to see how powerful this this Hadamard transform can be, let's look at the following simple problem, which is a parity problem. So we are given some function f from n bits to 1 bit, and it's given to us as a black box. So we are given a program that will compute this function for us, but we cannot look inside the program to see how it's doing so. All we can do is run this program on any given input. So program or a black box containing a circuit for computing this function f. Now, we also told that this function f has a very special property. All it is a parity of some subset of the bits. So it's of the form u dot x for some hidden u, which is an n-bit string. So for example, n might be equal to 3, u equal to 101, in which case what this function does is on input x1, x2, x3, so x is a 3-bit string, f of x is just x1 exclusive or x3. Right? It's x1 plus x3 mod 2. Okay. What we mean by u dot x is it's u dot x mod 2. So now this is the circuit that we have. It takes as input x, it outputs f of x, and we want to try to use this box to try to figure out what this parity mask u looks like. So classically, this is this is sort of easy to figure out. What you would do is you'd give as input. So you might first input 1 0 0 0 0. What's the output? Well, it's just u1. And then you could output 0 1 0 0 0 0, and the output would be u2. And so in n such steps, you can figure out u, which is u1 through u sub n. Can you do any better? Well, clearly not, because each time you run this circuit, you get only 1 bit of information. So you can conclude you need at least n steps, because you need to reconstruct n bits of information. So that's a classical situation. What about in the quantum world? Okay, in the quantum world, remember what we do is take the circuit and make a quantum circuit out of it. So now it takes as input x and also an input b, which is the answer bit. And what the quantum circuit does is it outputs x and b XOR f of x. So the output, the answer bit gets toggled if and only if f of x equal to 1. I'm suppressing the work bits because they start at 0 and end at 0. Now, of course, quantumly we can also input. We can put x in superposition, so our input could be sum over x of alpha x get x, and the output is now going to be sum over x alpha x get x, but then we have the answer in superposition f of x as well. Okay, so can we reconstruct u using fewer queries to f of x? So we needed n such queries in the classical case. Can we do it in fewer queries? And it turns out the answer is yes. There's an algorithm that does this using as few as 1 query to this circuit for computing f in the quantum case. And so the strange part here, the counterintuitive part here is that even though the circuit is outputting 1 bit on 1 bit of information, we seem to be getting n bits out of it. Okay, so how does this algorithm work? So it works by first setting up a particular kind of superposition, which is a superposition over all n-bit strings x of x with this phase -1, with a phase of -1 if and only if f of x equal to 1. Okay, so this we'll call the phase state, and now what you do is you do Fourier sampling and you obtain u. So let me first explain why the second step works. You see, because f of x is just u dot x, so this superposition is just 1 over 2 to the n over 2, sum over all x, -1 to the u dot x, x. Now remember, what is this state? Well, this state is exactly what you get if you do the Hadamard transform on input u. So if that's your input, then this is what your output is. Okay, so what we want to do is we want to run this circuit backwards. We want to run the Hadamard circuit backwards, because we want this as input and we want that as output. So how do we do that? Well, remember, the Hadamard transform is its own inverse. So all we have to do is we have to put this input through the Hadamard transform again. We'll get this as output, and then we just measure, and we'll obtain this hidden u that we were looking for. So the only thing we have to do now is to figure out how to set up this superposition. Okay, so how do we set up the superposition? Well, this is actually not that difficult to do. So what do? Well, we start with n bits in the 0 state. We perform a Hadamard transform on them. So now if we start with 0 to the n, we perform the Hadamard transform. What do we get? We get sum over all n-bit strings x of x with amplitude 1 over 2 to the n over 2. Now what we do is we set up the answer bit in the state minus. Okay, so the answer bit b is in the state minus, which is 1 over square root 2, 0, minus 1 over square root 2, 1. Now, if the answer... Okay, so what happens if f of x equal to 0? Remember, the answer bit becomes b XOR f of x. So what's b exclusive or f of x in this case? Well, it just stays minus, right? Because when you XOR 0 into something, it does nothing. So it just stays 1 over square root 2, 0, minus 1 over square root 2, 1. What happens if f of x equal to 1? Then b XOR f of x is just, well, you toggle it, right? So you get 1 over square root 2, 1 minus 1 over square root 2, 0, which is just, you pick up a phase of minus 1. So that's what we are doing. We set up the answer bit as a minus, and then we are running the circuit for computing f. So remember, the input to the circuit is a superposition over all x. And what happens when we compute f of x with the output bit, the answer bit set as minus? Well, whenever for those x such that f of x equal to 0, the phase doesn't change. And for those x such that f of x equal to 1, the phase changes to minus 1. Okay, so what's another way of saying it? So at this point, our superposition was sum over all x, 1 over 2 to the n over 2, plus, sorry, x, and then our answer bit was set as minus. And now when we compute u sub f, we'll go to sum over all x, 1 over 2 to the n over 2. And then we still get x, we still get minus, except that whenever f of x equal to 1, we pick up a phase of minus 1. So we get minus 1 to the f of x. Okay, but this is always minus, so this is always a tensor product state. And so if we look at these qubits, the first n qubits, we've got the desired phase state, which is that. And now if we do another Hadamard transform, we end up with our with u. Okay, so this gives us, this is really the algorithm. We set up n qubits in the 0 state, answer qubit in the minus state, we perform Hadamard transform, perform u, now we've set up the phase state, we do a Hadamard transform on the first n qubits, and we recover u. So we measure. Okay, so this algorithm was really the base case of a recursive algorithm. This recursive algorithm is called recursive Fourier sampling. I'll just give you a very short sketch of it, not really enough to explain it to you, but just tell you the basic idea. So in this recursive version, we solve a recursive version of the same parity problem. And now we are trying to amplify this difference between classical and quantum. In the classical case, you needed n queries. In the quantum case, you needed only a constant number of queries. And so what you do is, in the recursive version of the problem, classical algorithms satisfy the recursion that time to solve a problem of size n is at least n times the time to solve a problem of size n over 2 plus order n, where this n is the number of queries required to solve the parity problem. If you solve this recursion, you get T of n grows at least like n to the log n. So this is super polynomial. If you work through the quantum algorithm for the recursive problem, it satisfies the recursion T of n equal to 2 times T of n over 2 plus order n, whose solution is T of n equal to n log n. This is like the recursion for merge sort. And so you get a polynomial time quantum algorithm. And so this gives you already a glimpse of this power of Fourier sampling, that it gives you a super polynomial speed up for a certain kind of problem. Okay, so in the next video we'll see how to use Fourier sampling in an even more dramatic way.